Hey everyone, welcome to our channel where we will break down the IB Math AHL syllabus into bite-sized, easy to understand videos. If you're about to start the IB diploma and want to get a head start, you're in the right place. This is the first video in a 5-part series where we will quickly go over the key topics in the syllabus. And today I'll be covering the first topic, numbers in algebra, which is a core foundation of the IB Math AHL. So by the end of this video, you have a good idea of sequences and series, logarithms, complex numbers, and mathematical proofs. Plus, we'll finish off with an example problem on proof by induction, which is an area where most students struggle. So first up, we have sequences and series. A sequence is simply a list of numbers following a pattern, and a series is the sum of terms in a sequence. So we mainly focus on two types of sequences. The first one is arithmetic sequence, where each term increases by a constant difference that we can call d. So for example, you can have a sequence that looks like this: 2, 5, 8, 11, and the constant difference d is 3, because it goes up by an increment of 3 every time. And geometric sequences is where each term is multiplied by a common ratio that we can call r. So an example would look like this: 3, 6, 12, 24, and the ratio r is 2. 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24. So in both cases, there are formulas that can help you find the nth term of the sequence, or the difference, or the first term, or any term in the sequence. And the formula booklet that the IB provides has these. So for arithmetic sequences, the formula is as so. And for geometric sequences, this is what the formula looks like. So IB math questions about sequences will usually involve these formulas, because they're the most basic formulas. But you can play around with them. You can, for example, you can say un minus u1 divided by n minus 1 equals d. So that can help you find d, for example. So in HL Math, you'll also encounter sigma notation and sum formulas, which help us to calculate large sums efficiently. So again, the formula booklet provides these formulas. So for arithmetic sequences, if you want to find the sum of n terms of an arithmetic sequence, you can use these following formulas. So there are two formulas, and you have to decide which ones you want to use based on what the questions provide you with. So this is the first one, but this is also equal to n over 2 times u1 plus un. So let's say the question that you're faced with gives you the common difference. Well, you'll definitely use this formula because it has d, the common difference, so it'll help you find the sum of n terms. So for geometric sequences, it's a little more difficult. It's either a sum of n terms of a finite geometric sequence or an infinite geometric sequence. So for finite geometric sequences, again, there are two formulas that you can use to find the sum of n terms. To find the sum of n terms in the sequence. So this is the first formula, and another formula you can use is this one. So again, they have the same purpose. So this is for a finite geometric sequence. Now, if we're talking about an infinite geometric sequence, we can name that sequence S subset infinite, and this is equal to u1, the first term, over 1 minus r, the common ratio, considering that, of course, r is smaller than 1. So this is a formula you can use for infinite geometric sequences, and this is also provided in the formula booklet. So now let's talk about logarithms. So this is the opposite of exponentiation. So if a to the power of x equals b, then we can write this as log a of b equals x. So there are some key logarithm rules that you have to memorize. Some of them are in the formula booklet, but I'll just give you a few here. So with the product rule, and so this goes as so: log a of x times y two values. This is equal to log a of x plus log a of y. A similar one is quotient rule. Again, these are very basic rules. If you took math, I think even standard level in year 10, year 9, you should be able to do this. You should know this already. So x over y, again, two values, but a quotient this time. This is similar. It's log a of x minus log a of y. And finally, the power rule. Log a of x to the power of n equals n log a of x. So you'll use logarithms a lot for solving exponential questions, especially in calculus and modeling real-world problems. So now let's explore complex numbers. You've probably seen I somewhere in math. Maybe you have seen it already, maybe you haven't. This is the imaginary unit. So I squared equals -1, or I equals square root of -1. So square root of -1 isn't really possible in mathematics. So this is why we call it imaginary. So there are a lot of things to know about complex numbers. The formula booklet does provide a little formulas about complex numbers, but I do feel like there are some basics that you have to know, so I will be showing this in this video. So first, again, you know that I equals square root of -1, and a complex number can be written as z equals a plus bi, where a is the real part and b is the imaginary part. You should also know that z asterisk means the conjugate of the complex numbers, so a minus bi. The modulus form of the complex number is r, which is square root of x squared plus y squared. And this will be helpful when we come to De Moivre's theorem. So going into the algebra of complex numbers, when we have a division, so complex numbers can be written in two main forms, Cartesian / rectangular form, where the complex number is written like this, or modulus argument or polar form, where it's written like this. So let's say we have the complex number in rectangular form, 6 plus 4i. So if we put this on a graph with the axis real and imaginary, so we would have 6 here on the x-axis and 4 on the y-axis. So if we extrapolate here and draw a line to this point, this gives us an angle theta, and this angle theta is going to help us to transition from rectangular form to modulus argument form. So modulus argument form looks like this: r cos theta plus I sine theta. So we already have theta. Now what is r? R is the modulus, and if you remember from what I said previously, r equals square root of x squared plus y squared. So having both r and theta, we can plug this in this form, and then we'll have our modulus argument form, with the modulus being this and the argument being this part, which can be written as cis theta instead of cos plus I sine theta to go faster. You should also know that multiplying complex numbers, so let's say z1 times z2 is equal to r1 times r2 in the modulus argument form times cos theta 1 plus theta 2, so not times theta 1. It's not a multiplication in the angles, but it's theta 1 plus theta 2, and this goes the same way for I sine theta 1 plus theta 2. If it's a quotient, it's going to be the same thing, except it's going to be theta 1 minus theta 2. So these are important things to know, and this might be helpful in a few questions that you're faced with on complex numbers. So finally, we reach mathematical proofs, a big part of IB Math HL, and you'll learn different methods to prove mathematical statements rigorously. So there are 2 to 3 major ones, but I will be including proof by deduction, which is a simpler type of proof. So I'll start with this one. So proof by deduction states that LHS equals RHS. So let's say you have a question that says, show that x plus 1 to the power 4 equals or is equivalent to x to the power 4 plus 4x cubed plus 6x squared plus 4x plus 1. So this is considered the LHS or left-hand side, and this is considered the RHS or right-hand side. So looking at this, you're either going to want to simplify this or develop this. So the easier way to do this would be to develop the left-hand side. So where you're going to state is that RHS equals this thing here. And then you're going to go and say LHS equals x plus 1, 4, which is equal to, and then you develop till you reach what looks like what you wrote here, RHS. And then you can state that LHS, if you did it right, equals RHS. So the 2 other major proofs that you see in Math AHL in most, let's say, difficult questions, or at least that most students struggle with, are proof by contradiction or proof by induction. So proof by contradiction is where you assume the opposite of what you want to prove, and it showed that it leads to a contradiction. So an example is proving that square root of 2 is irrational. You're also going to have to know basic things like even numbers and odd numbers, how to represent them, because most questions from IB past paper questions are usually about odd numbers, even numbers, or irrationality, rationality. So for even numbers, you're usually going to want to represent even numbers as 2k, for example, and odd numbers would be 2k plus 1. And so that's going to be very helpful in your demonstrations of proof by contradictions. If you want to represent a rational number, you could say that your rational number would be a over b, where a and b are integers and they have no common factors, and of course b is not equal to 0. You also might want to know that if there are 2 sides of an equation with different factors, they are not the same multiple. So that's going to help you in some demonstrations of proof by contradiction. So now on to proof by inductions. Proof by induction is used to prove statements for all natural numbers. So it has a very defined and clear way of doing it. So the first step is to say that you're going to try with 1, the first natural number. And then it's pretty easy. The second step, you try with k. And then, so you replace whatever the equation you're given. Let's say it's like 2n minus 1 equals n squared, which would say that, prove that the sum of the first n odd numbers is n squared. Then you would replace n with k, and so you would have 2k minus 1 equals k squared. Of course, this goes for 1 as well. If you replace 2n minus 1 equals n squared, if you replace the n with 1, it would have been n times 1 minus 1 equals n1 squared, which is 1 equals 1, so it works. So let's say now you have, you tried with k, 2k minus 1 equals k squared, and then you're going to try, well, you don't write try, you're supposed to, right, assume true. You assume that it's true for n equals k plus 1. N equals, and here as well, not for the first step, only for the second and third step, you assume that it is true for n equals k, n equals k plus 1. So here again, you're going to replace n with k plus 1, so 2k plus 1 equals k plus 1 squared. And then you develop, and what you're going to try to do is show that you want to get to the conclusion that since the first step is true, and that the third step where n equals k plus 1 is true, whenever n equals k is true, then the sum of the first n odd numbers is n squared. So that wraps up our first topic, numbers in algebra. We covered sequences and series, logarithms, and complex numbers and proofs. So in the next video, we'll move on to functions, which is one of the most important topics in IB maths. So if you found this helpful, you can interact with us, like, subscribe, drop a comment if you have any questions. And yeah, see you in the next one.